Alright, where were we? I think I was just going through this equation here. Yeah, that's the yield capacity of the rings of steel. So for N bars, it's 500. So let me adjust this a bit. Okay. Our BV, we've already got. FC, so we've got all the terms here. So let's put this in. ASV minimum equals, now we're going to take the spacing up to that side, equals 125 times 0.08 times the square root of 40 times 300, all divided by 500. And if I put that into a calculator, that is 125.08 40 square root, all right, 300, multiply that, divided by 500, and that gets me 37.9 square millimeters. Okay, now 37 ASV min is 37.9 square millimeters. Okay, what that number actually means is, when we look at our front page again, if I do a cut, an imaginary cut through there, the amount of steel crossing that cut for every ring has to be 37.9. So half of 37.9 is there, the other half of the 37.9 is there. All right, let's see how much steel we've got. We've got N10 bars. Each of our bars, for an N10 bar, is 10, divide that by 2, it's 5 millimeter bar, we'll square it, times pi. We have, oh, and then we've got 2 of those, 157 square millimeters. So we are comfortably more than the minimum steel. So now we're going to go back to over here. So our simplified thing here, we're going to find KV. Our minimum steel is greater than, our steel is greater than the amount of minimum steel, so our KV value is 0.15. That was a long detour, wasn't it? KV equals 0.15, and that comes from clause 8.2.4.3. 8.2.4.3. Alright, we've got to number these pages so we don't lose them. Page 1, page 2, this is page 3. We're about to start page 4. There are some more to come yet. Alright, so now we go back to our VUC from our last page, and we were looking for VUC is KV times BV times DV times F-C. We've got all those terms now. So I'll write it out again just so we're not confused. Equals KV, BV, DV, F-C. So KV equals 0.15. We've just found that. BV is the bottom width of our beam, 300 millimeters. DV is that shear depth. You recall we worked that out quite a while back. That was on the first page here. That is 360 millimeters. And our F-C, of course, is 40 MPa. All right. So look at those terms. There's a constant. There's the area of the beam if you multiply it by those two, and there's the concrete. This is the shear capacity of concrete. So it's no surprise that the steel doesn't come into it. Let's multiply that out. We get 0.15 times 300 times 360 times the square root of 40. And that gives us 1 102,457 newtons, which is 102 kilonewtons. VUC equals 102 kilonewtons. All right. So you recall earlier that if our shear load was less than 5 times that, you don't need it. You don't need any shear steel at all. So if our shear load was less than 0.75, let's go 0.75 times that, is 76.8 kilonewtons. If the shear on this beam was 76.8 kilonewtons and there was no torsion, you would not need any rings in this beam at all. Okay? And also, while we're here, remember that when you have a beam, say you have a beam under normal bending, okay? You have a beam under a distributed load like that. The shear force diagram for that is going to equal, if I can draw the shear force diagram, draw it in color for you. The shear force diagram for that, as you know, is quite high at the supports and comes down to a very low number in the middle. And so what you might find is when you do a shear thing, you might only need shear steel in the ends of the beam there, and in the middle of the beam you can get away without it at all. Okay, so there's parts, often areas in the beam where you don't need shear steel, where you do. And when you come to situations like this, there are rules about how far beyond that point do you have to carry the rings, and that's in the details about detailing reinforcement. But let's get back to our point. Obviously, our V star equivalent, we worked that out back here, was 210.3. Therefore, we need rings. And I'm using all these different terms interchangeably, sorry. All right, so let's work out what VUS is. Okay, VUS is the shear capacity that you get by having steel rings. And that's in the equation. That's on the next page here. Oops. 8.2.5.2. All right. Clause 8.2.5.2. For perpendicular shear reinforcement, for inclined shear reinforcement. All right, what you can do, the vast majority of times you build with concrete, you put the shear rings at 90 degrees, that is vertically. You put them vertically across the beam, and that's how they work. What you can do, if you're trying to be clever, is actually tilt those rings slightly, and if you tilt them the right direction, you get some additional capacity. All right, and that's what this comes in here. We're not going to tilt them, certainly not today. In the vast majority of cases, you wouldn't bother doing it because it's a bit expensive to do it, and there's easier ways to get more capacity, but that's a bit of a trick if you want to go that way. So VUS, where are we? Equals ASV times FSYF times dV all over S times cot theta V. All right, let's go through each of those terms. ASV is the area of steel in each stirrup. In a single loop stirrup, you've got 2 bars which cross the plane. Remember I said when we cut that area there across there, how much steel crosses that cut? Sometimes in very large beams you'll have more than one loop, so you might have 4 there. But we've got 2 bars, they're N10, and we calculated out just before that our steel is 157 square millimeters. So you can do that with a pi r squared, or you can look it up in the reinforcement book. But that's the area of steel crossing that section. So it's one bar there, one bar there. All right, FSYF, same thing as before, 500 megapascals. DV, same thing as before, 360 millimeters. S is the spacing of these, how many rings you need. If you're trying to work backwards, sometimes you work out what the S needs to be in order to get that. But we've nominated 125 millimeters. All right, and that leaves us with this little term here, cot theta V. And this theta V angle is one of the complexities that we touched on before. And what the theta V is, it's an angle that the shear force makes in the concrete when you're doing a strut sort of analysis of it. So here it is down here, it's 29 plus 7,000 times the epsilon x, where the epsilon x has this big equation down here with all the other terms in it. Within the limits are there. It's a very big term. But again, in the simplified method, as long as we comply with all those conditions that we read out earlier, we can use a theta V as 36 degrees. Okay? 36 degrees. And that is the simplified and slightly conservative method. All right, now you notice we take the cotangent. That is, the cot of an angle is 1 over the tan that angle. Cot theta equals 1 over tan theta. Okay, so if you look on your calculator and you can't find a cot button, what we're going to do is go 36 degrees tangent and then take the inverse of that. And so cot of 36 degrees is 1.376. Now, you can use Excel for this. Just put cot and then the angle in Excel and you'll get the answer. Be careful because Excel defaults to radians and we normally work in degrees, so you've got to convert the degrees into radians first, okay? A way to check it is cot of 45 is 1. Because tangent of 45 is 1 as well. All right, 1.376. So therefore, we're going to get our answer. 5 VUS equals area of steel, which is 157, times 500, times 360. Close the brackets, put that over 125, times 1.376. Equals 157. We get 31172, and that again is obviously in newtons. So VUS equals 311.1 kilonewtons. We are on the home straight, guys. Hang in there. All right. So now we have VUS. We have VUC. We can work out phi VU, the whole capacity of the beam, equals phi times VUC plus VUS, and that equals 0.75 times, where is that VUC? Back there, 102, plus VUS, which we just worked out, 311 plus 102, multiply all that by 0.75, and that gives you 309 kilonewtons. 5 VU equals 309 kilonewtons. 309 is greater than our V star equivalent. You remember what that was? 210.3. 210.3 Okay. All right, so we've just proved that this can take the load. Okay, there's a couple more things to tie up before we get there. First is we have to check VU max. VU max is back here. VU max is if the concrete is not large enough and this whole thing collapses, then that's limited by VU max, and no amount of steel you put in there is going to fix that. Okay? VU max. That means you cannot take the capacity of this beam as anything greater than VU max. VU max equals 0.55 times F-C BV dV. We've got cot theta again, plus cot alpha over 1 plus cot squared theta plus PV. PV is our pre-stress, that equals 0, so we're going to ignore that. That alpha, do you remember we talked about the sloping rings? That angle, that's that angle there. So if your rings are at 90 degrees, cot alpha is 0. Because 90 tangent of 90 is undefined. You do the inverse of that, cot of that is 0. So that's pretty easy. Okay, everything else we've got the terms for. So that equals 0.55 times 40 times BV was 300 times 360 times, whoops, cot theta was 1.36, we did that earlier, over 1 plus 1.36 squared. By the way, mathematically, that cot squared theta, basically you just take cot theta and then you square it. That's how you write that in maths. That's all. So that is going to equal, I'll calculate that out now. Oh, and that's plus 0 because the cot alpha, as I said, is 0. 300, 360, 1.36, 1.36 squared plus that. Okay, so we've got 0.47, we multiply that out, and 0.55, and we get 1133969, which newtons, of course. So VU max equals 1,133 kilonewtons. We have to make sure our capacity is below that. Our capacity is 309, this is up at 1100, no problem. Okay. If, by the way, you do get a problem here, the only way to fix it, the main way to fix it is to get a bigger beam. If you want to play around the edges, if you increase the concrete strength, it gets bigger. That's about all you can do unless you start angling your stirrups. Okay, we are near the end. Now, you may be thinking to yourself, why did I over-design this to this extent? Well, if we increase the spacing of those stirrups, we could go to pull the stirrups out to 200 millimeters, and that would, let's work it out. If that was 200 millimeters, then that, instead of being 125, would be 200. So we could go 157, 500, 360, 1.376. Multiply all that, divide that by 200. If it was 200, then our N would be 194. Okay, so our VUC plus VUS would be 194 plus the 102, which is 296 times 0.75. We would have a phi VU of 222. And that would be a lot closer to our 210. So that would be a more efficient design. However, because we have torsion, we have some more restrictions on these rings. And this is why that 125 came in. So you come towards the back here, and you come to, there's a big section on, that already, where was it? Detailing of this stuff. Proportioning longitudinal reinforcement, no, it's not that. General detailing for beams. Okay. This is all about, detailing is all about how long this has to be, other rules that you've got to comply with. And here's the thing about without torsion. So, okay, without torsion, the maximum longitudinal spacing shall not exceed the lesser of 300 and 0.5 D. So with our beam of 450, half of that is 225. You're not allowed to have those rings any more than 225 apart. Okay? And then over here, torsional reinforcement should be detailed in accordance with that previous clause and this. And the closed fitments must be no greater than the lesser of 0.12 UT and 300 millimeters. All right, the UT, what's that? That is defined back here somewhere, and I think it is the area of, I'm sorry, it's the perimeter. Better look it up, because I've forgotten where it was defined. Hang on. If you want to look up any of these terms, you come to the front of the code, and all the terms are laid out here. So they're in alphabetical order, so you get to learn your Greek alphabet as well. And U is the length of the outside perimeter of the critical shear area. So it is basically the diameter of that bar, not the diameter of the bar, the diameter of the ring that the bar makes. So UT equals, what we had before is 360 minus 30 minus 30 minus 5 minus 5, which is 70 minus 80. Sorry, 360 minus 70 is 290. That's one side, and then 450 minus 30 minus 30 minus 5 minus 5 is 380. So they're the sides, so the perimeter, whoops, UT equals 290 plus 290 plus 360 plus 380, sorry, plus 380, which equals, that 290 can't be right. It was, sorry, 300. That was that. So it was actually 230. It's obviously getting late. I have not had enough Tim Tams. 230 plus 230 plus 380 plus 380. Hopefully that's right. 380. It's those sort of stupid mistakes that'll get you. So add all that up, I get a perimeter of 1220 millimeters, and I go 0.12 that, so 0.12 UT equals 146 millimeters. So therefore, rings must be less than 146 millimeters apart, and you generally go to the nearest 25 millimeters, so therefore N10 rings at 125 millimeters center to center. Alright, so if we did not have the torsional forces on, I could use a lot less reinforcing steel. Because we do have the torsion forces, we've got to comply with that rule, which actually exceeds all the strength. So there we go. We have worked out the torsional capacity, or shear capacity, I'm sorry, of that beam. So most times, obviously, you approach it a different way. You've got these loads and you don't know how much steel you've got to use. The way to do it is to put something sensible in and then see if it works, and then work from there. This is where the beauty of spreadsheets and other programs come in, because you can play around with numbers. But that's the process you got to go through. Ain't concrete fun.